and I'm happy to have Steve here, and as you want to be a bit of me, I will take over.
Thank you very much, Mike. And thanks to those of you who decided to stay. I should apologize in advance. I have bronchitis, so I'll be coughing periodically. Sorry about that. All right, let's get started. Programmable devices. Well, we want to build something better than an FPGA. Let's look at today's programmable devices. As far as I'm concerned, there's good news and there's bad news. The good news is, well, they're programmable. That's a great thing. You can change it, set a chip into whatever you'd like it to be. And historically, programmable devices are always on the leading edge process, taking advantage of the best manufacturing available. The bad news is FPGAs just aren't very good. They're very expensive, and they're very large, and they're very slow, and they're very power hungry, and they're very hard to program. And what's worse, they're controlled by a duopoly, which in this talk I'll refer to as Cytera, since we know they make the same product. Excuse me. Can we do better? And the answer is we can. To try to motivate this a little bit, let's start about how we're going to get from an FPGA to what we call a 3PLD, a three-dimensional programmable logic device, as follows. Suppose you have an FPGA, and it's a two-dimensional device, and I'll put on a grid so we can see what's going on a little more easily. And you have a LUT on that FPGA, and you have a second LUT on that FPGA, and the one sends a signal to the other that takes, for the sake of argument, 1 nanosecond. Let's look at the same picture in a slightly different way. We're going to look at this picture in 3D, where our third dimension is time. Still talking about an FPGA. First, we're going to look at the LUTs. Since a LUT gets its program, and then it keeps that program for all of eternity, the way a LUT looks like in that 3D space is a column of infinite height. But what does the wire look like in this same picture? We know that it's L1, and at L1 at time 0. We know that it's at L2 at time 1 nanosecond, and it's going to go presumably in a straight line from the one to the other. Therefore, that wire looks like a diagonal in this three-dimensional setup. Make sense? The interesting questions become, well, given that L1 was necessary only for a couple hundred picoseconds to do a computation, and after that was going to sit there twiddling its thumbs for the rest of the user cycle, and given that L2 has nothing to do for most of the first nanosecond, then it does its job in a couple of tens of picoseconds, and then it's going to sit there and do nothing for the rest of the cycle. Can we use this real estate more efficiently? The interesting question is, what should go in that space in this picture? What we claim is that instead of doing what an FPGA does, which is to put L2 there, when we've already established the L2 sitting there is doing absolutely nothing. You can't execute anything at L2 that's interesting at the beginning of the cycle. You're going to wait for most of the nanosecond. We're going to put a different LUT there with an entirely different identity. L3 computing something completely different from what L1 and L2 computed. Going back to our 2D picture, what that L3 sits right on top of L2, but has a different program. That L3, in turn, can do a computation, and it sends a value to L4, which in our 3D picture looks like this. So the point is that by reusing the logic of a different LUT, by putting multiple programs per LUT, but also by looking at it in this 3D space, we can use the 3D space in which that computation lives in a much more efficient way. Now, when there are only 4 LUTs, it's still possible to keep track of what's going on in the 2D part with the physical device and the programs, and what's happening on the 3D view of that part, where you have these different LUTs living in space and time. As you get to 100,000 LUTs, or 500,000 LUTs, or 1 million LUTs, it's much more difficult to track what's going on. So what we're going to do is view that third dimension as a real spatial third dimension. Even though it's made out of time, we're going to treat it as though it's made out of space, and build our system in an XYZ three-dimensional space. So I can now populate that three-dimensional space completely freely with LUTs and muxes and wires and so on. We can treat this device as a full-fledged 3D device that can do full-fledged 3D computation, where I can put any one of my objects in any X, Y, Z location I like. I have the complete freedom of that third dimension that I had in the other 2 dimensions when I was working on the FPGA on the right. Just for interest, here's what that same picture looks like on the right, and good luck keeping track of it when you have all of these LUTs and muxes and stuff on top of each other. Our experience, and we've worked on this for more years than most of you, is it's just too hard to track what the heck is going on with this kind of setup without viewing this in this 3D way. Just imagine that the 3D objects persist for all time, that it is though you have spatial LUTs and spatial muxes in this 3D. That intuition won't fail you The mathematics is appropriate. It makes placing out easier, as you'll see later in the talk. This is really the only, in my opinion, the only sensible way of talking about this sort of dynamically reconfigured device. Now, last couple of details to mention here. The x and y dimensions are pretty much discrete. There are only particular physical locations where an individual LUT or an individual MUX to be on the physical device. But we can treat our z dimension as continuous. Because it's actually a t dimension, I can schedule a LUT or a MUX to execute anytime I like. I can have arbitrarily fine resolution in principle about when it is that a particular computation occurs. And we can make use of the continuous nature of that third dimension. And one last thing, just by way of intuition, this is what a critical path looks like in space-time, as we call this technology, space and time. And as you'll see, the space-time that we have is, in a very literal sense, equivalent to the space-time that you see in special relativity from Einstein, which is exactly why we call it space-time. It actually is space-time. Anyway, this is what a critical path looks like. And you can see that we want to try to put LUTs directly on top of each other in C so we can waste no time between them. You can, of course, look at that same critical path in 2D and good luck figuring out what's going on at 3D time. So our approach has been view this problem as though we have the full freedom to place and route our objects in 3D and use that as a way of reasoning about the system, use that as a way of building software for the system as well. You know, a little bit about this dimension stuff. It doesn't surprise me at some level. Many times we'll talk about stuff like ours as having a virtual third dimension. But you guys are technical people and know better, and know that what we have is actually three-dimensional. It's not virtually three-dimensional in the following sense. First of all, dimension has an actual definition. How many coordinates do you need to specify? And the fact is, it really takes 3 coordinates to identify any of our LUTs or any of our MUXes. You have an XY location, and you have which of the programs you're going to execute. So it really does take XYZ or XYT to identify which particular computation, which particular MUX, which particular LUT, which wire you're referring to on our part. This is what it means to be three-dimensional. Space-time is literally three-dimensional. Now, by comparison, FPGAs, which have only one layer of LUTs, one layer of MUXes, are 2D. Not 2.5D, not 3D, 2D. Like ASICs, they have multiple layers of interconnect, but they have only one layer of their LUTs and MUXes, and you can identify each with just 2 coordinates. And that still happens when you have interposers and you end up making a big, wider FPGA. Okay, the interposer is a nice thing, it gives you some additional layers of interconnect, but you're still in 2D. Not 3D, not virtual 3D, not 2.5D. And for those of you who are interested, this is what a 2.5D system looks like. That too has a well-defined mathematical representation as existing devices. Okay, let's return to space-time. So let me talk a little bit about the implementation of the cars. So we have devices with some number of planes of computation that we call folds. And what's happening if we have a device with, say, 12 folds, is that under the covers, we have a very high-performance clock that can go up to 2 gigahertz, a high performance even by ASIC standards. And what happens is that during your computation, even though we present it to you as this 3D device with those 12 floors, in fact, what's happening on the chip, under the covers, hidden from you as a user of the technology, is that if you have, say, 166 megahertz user clock, that's what makes the math easy, is we take the first 12th of what would have been computed in your 166 megahertz clock and execute that first. Then, holding that state somewhere, more on that later, we reconfigure the entire device, all the lines, all the MUXes, all the LUTs, all the everything, are reconfigured to begin the second 12th of your computation. And then reconfigure again to do the third 12th of your computation, and so on. This gives us the ability to reuse every single thing on the chip up to 12 times, which means that we can build a much smaller device and a much faster device to do your computation, and you'll see how that manifests in the brain. One detail that's important to point out is that our third dimension is a little weird in that not only is it unidirectional, because time is apparently it's unidirectional, but also we're on a torus, because at the end of each cycle, you're going to start the next cycle. And so what happens is at the end, you come around the torus. So we have 2 spatial dimensions and then a third dimension that's actually a torus. And we'll see more about that later. Now, before I go on, let me set a little bit of context. We are not the first people to talk about dynamically configurable device. The fact is, Turing in the 30s was fascinated by the idea of self-modifying code and talked at some length, actually, about reconfigurability and the benefits you could get from a reconfigurable device. So this is an old idea and one that's not new to us. Applying this in a FPGA-like context, I'm not clear who's first with that, but I would say it's DeHon, most likely, who took the first serious whack at it with his pioneering work at MIT. And after that, you have a bunch of efforts in companies big and small that basically failed to try to take that fundamental idea and make something useful and practical. What we've come to learn is that the reconfiguration part is trivial. That it's a nice idea. As it happens, I thought of it myself, independently of those other folks, but a bunch of other folks have thought of it too. That's the easy part. The next 600 problems that happen after that are much harder, and the 600 after that are worse still. And I'm going to talk about what some of those problems are. So just as a sampler platter here, I guess I'm a smorgasbord country. How do you close timing? How do you achieve high performance? The time to reconfigure, doesn't that kill you? Where does the state go while you're reconfiguring? How do you have user designs to this fabric anyway? Do you have to change methodology in some fundamentally different way? How do you have multiple clock domains? And how do you interact with asynchronous domains in this hyper-synchronous fabric? How do you make memories work in a dynamically reconfigurable device? And the power, isn't that going to be awful if you have a 2 gigahertz clock? I'm just getting started. I can have 5 slides of a list of problems like this. How would you build an analytical placer in space-time? How do you have related clock domains talk to each other? How do you build a router, minimal spanning trees, Steiner trees? Parenthetically, those problems are much harder than they look in space-time. Excuse me. How do you account for that reconfiguration time? Does synthesis need to care about space-time? Can you do clock gating? And if so, what does it look like? And how does DSP work? So like I said, I can go on for slides and slides. What I'll point out here is that the list of problems like this have either been unidentified by the community before us, trying to do reconfigurable devices of some sort, were answered incorrectly, or were answered insufficiently. And I won't have time to talk about all of them today, obviously, but I'm going to hit most of the ones on the left, at least briefly, during the next talk, if I can, without having minutes reflect. Okay, let me set a little bit of context. The context is, so we have this 2 gigahertz clock on here. We should be able to do some pretty cool stuff with the 2 gigahertz clock, besides the fact that we're reconfiguring the logic. What might that be? Well, the fact is, let's look at how many folds you might want to use, so how many times you're going to reuse each object per user cycle, and how many megahertz you're trying to run it. If you're building an FPGA, well, you're stuck with 1 fold, and going more than 300 megahertz or so is very, very difficult. But suppose you want to do DSP functionality at 2 gigahertz, as you might on a high-performance DSP device of some sort. We can actually do that. We have an actual 2 gigahertz clock. We have an actual 2 gigahertz DSP. We can actually run the stuff at 2 gigahertz. But that's only a small part of what you're usually trying to compute. What if you have an ASIC or ASSP-style data path? That might be running at 500 megahertz. Interestingly beyond what you can reasonably do on an FPGA, but a perfectly reasonable thing to do on an ASIC. Well, we're running at 2 gigahertz. To us, 500 megahertz just isn't that fast. In fact, we can reuse everything 4 times and still get stuff done at 500 megahertz. So what that means is, we don't need much real estate at all, and we can still get your 500 megahertz logic to work. Okay, how about FPGA class stuff that's running at 250 megahertz? We can run everything 8 times and still get the work done, which means that we don't need very much real estate at all to do 250 megahertz logic and get that logic done, because we can reuse. And finally, the control logic, which is often slower than that, a soft microprocessor at 150 or 200 megahertz, there we can get 10 or 12 reuses, so that can be really tiny. So the point is, AVAX, the name of our chip. This is basically what we're doing. We're exploiting the fact that you give us some design. It has some specification in RTL, and we know what you're trying to implement, and we know how fast it's supposed to go when you have your multiple clock domains. We can make fast stuff run quickly, really quickly, 2 gigahertz quickly. And we can take all the other stuff, which is most of what you have, and make it really tiny, because we can reuse everything multiple times. And our software automatically makes that trade-off, so that you just give us the specification of your design, and you automatically figure out how to map it. This is one of the things that something like Spacetime can do, is to make that sort of trade-off dynamically and automatically at all times. Now let's talk about a whole different aspect of this, memories. As anybody who works on FPGAs knows, in addition to logic, you of course have block RAMs of various sorts, and we too have block RAMs on our chips. But it turns out you can do some pretty darn cool stuff with RAMs in a space-time setting, something nobody else seems to have noticed. So we're back in our XYZ coordinate system. We have our folds. We have our logic and our interconnect. And then there are block RAMs, physical RAM circuits somewhere on the chip. But of course, you want to hold those bits from user cycle to user cycle, so presumably the values of those bits are going to persist in time from cycle to cycle, so they look like little skyscrapers as drawn in this picture. Well, the way that manifests is that you can reuse that memory multiple times within one user cycle. So we can basically treat each one of those folds as different ports on the same memory. Let's see how that works. So I have a memory, and in fold 0, there's some amount of logic that can talk to that memory. And then again, in fold 1, some totally different piece of logic, which is what's living in fold 1, can now talk to that memory. And again in fold 2, and so on. So what that means is I get as many ports as I have folds. And they're all running at 2 gigahertz. So I have unbelievable memory bandwidth. We infer these automatically. So if you give us a single-ported memory that's running at, say, 200 megahertz, we might discover, gee, you know, a better implementation of that would be to make a dual-ported memory that runs at 400 megahertz, or a 3-ported memory that runs at 600 megahertz, or a 10-ported memory that runs at 2 gigahertz, folding your words in such a way that we're still maintaining your functionality, but making the best use of the packing of your functionality in 3D to get the best performance and area out of Spacetime. What this means is that for most of our memories, we can use single-ported RAM cells. As all of you know, FPGAs are built entirely out of dual-ported RAM cells for the block RAMs. Well, single-ported RAM cells are less than half the size of dual-ported RAM cells, and we can use them for almost everything because we can get multi-portedness by the fact that we have these multiple folds and use the memories multiple times. That we can do 2 gigahertz RAM access means we can do RAM stuff faster than most ASICs. What gates the performance of almost all computation on almost any fabric is the throughput of memory and the latency to memory. And Spacetime solves both of those problems. We can run 2 gigahertz in practice in real life. So more than 3 times faster than even what the data sheet says you can do on dual-ported FPGA memory. And that's pretty good for networking applications. More interestingly, from a computation point of view, and it's a fancy computer in some sense we're trying to build, 12 different pieces of logic can be adjacent to the same memory. If you have some central data structure and you want a bunch of different pieces of logic to be able to talk to that data structure, just have the memory sit like this and have one piece of logic here, one piece of logic here, and so on. The fact that we can stack lots of logic and have all of it be close to that memory lowers our latency and gives us incredibly high performance. And it means that our DSPs can run at 2 gigahertz in real life. We're not talking about the datasheet number that says we have a DSP that runs at 700 megahertz, but you're never going to see more than 300 megahertz in real life. This is a 2 gigahertz DSP that actually runs at 2 gigahertz because the interconnect runs at 2 gigahertz, the DSP runs at 2 gigahertz, and the RAM runs at 2 gigahertz, and we have umpteen real applications that can actually demonstrate this. It also means that you can take multiple user memories and fold them into one Spacetime memory, as long as they have non-overlapping bits in space and in time. In other words, you have 2 memories you want your logic to be talking to. We give them different bits because both of the sets of bits have to persist to the next cycle, and we can say, we'll talk to these bits in folds 0, 3, and 7, and we'll talk to these bits in folds 1, 4, and 11, just for the sake of argument. So that means these 2 things can coexist in one RAM. Well, that now means that we can have lots of pieces of logic be adjacent to lots of memories all at the same time. Again, improving throughput and improving latency. The lack of this is what has limited the performance of computation. Not just computation on FPGAs, which are stopped with dual-ported memories and terminal wires, but computation on microprocessors and multi-cores as well. You can't have enough different pieces of logic, enough to different memory, near enough to multiple memories at once. This is a problem that Spacetime solves, and Spacetime solves well. At the end of the day, programmable devices, FPGA-class devices, are about interconnect. Because despite the fact that we're using the same transistors, ultimately we're Intel, but in any case, essentially the same transistors as FPGAs use. And so FPGA transistors run really quickly too. The LUTs are fast, the RAMs are fast, the DSPs are fast, but you never get that performance in real life because everything on an FPGA is constrained by interconnect. And the interconnect can't run much faster than 250 or 300 megahertz under essentially any circumstance. This is the other problem, or another problem that Spacetime solves. Since absolutely everything on our chip is able to maintain that 2 gigahertz rate, the interconnect, the RAM, the logic, the DSPs, everything, we can really get 2 gigahertz throughput on large scale applications anywhere we need it. I'm not going to say too much about Stylus. This is our software to compile user designs into Spacetime. I mostly wanted to bring it up so I can present this name. This is a technical talk, not a marketing talk, honestly. Let's talk about how it is we can achieve high performance. So you have some sequence of computation. If you something, you send the values on. If you something, you send it. We're going to map this into Spacetime. Excuse me. So of course it looks diagonal because it takes time for each signal to transit at DXDT. We're going to make it up. question is, what happens at the end of fold 0? Let's say that these blue circles are lots for the sake of argument. What happens at the end of fold 0? Well, I need somehow to preserve the state that comes out of fold 0 so I can take that lot and reconfigure it in fold 1. Well, if I think like an FPGA designer, and not a 3PLD designer, so not like that, I think, oh, well, but each one of my lots feeds a flip-flop. I'm just going to have the flip-flop on the far side of the lot, hold the value, the flip-flop is closed in fold 1, I'm good to go. Unfortunately, let's now see what happens at this next lot. So we completed the third of those lots, we completed its computation, but we couldn't quite get through the fourth lot. Unfortunately, the flops are all right at the output pin of the lot. So what that means is I'm going to store the value at the end of that lot, and then that signal is going to twiddle its thumbs for the whole rest of fold 1, because it's only at the beginning of fold 2 that we're going to have reconfigured the fourth lot to be able to send its value. So this is a bunch of wasted time. But that's not all, because so fine. I won't be able to take that value until the beginning of fold 2, once the clock hits. But then I have the next lot who sends a value to his flop, which is going to cause me to waste more time, which means the next lot is going to cause me to waste more time, which means the next lot is going to cause me to waste more time, and so on. That accumulated, wasted time of the caused by the quantization into subcycles is the thing that gates the performance of a dynamically reconfigured device. You know, some previous papers talk about, oh, the time to reconfigure and pipeline the reconfiguration, but of course that costs too much power and so on. That's not irrelevant, but it's second order. The high order issue, which not only as far as we can tell has been solved, as far as we can tell has not been solved before, as far as we can tell this hasn't even been noticed before, which suggests that previous attempts to build a dynamically reconfigurable device just didn't get very far. This is pretty near in and is absolutely fundamental. You cannot build, in my opinion, a high-performance reconfigurable device without worrying about this problem. How do you not get killed by the quantization? So let me talk about what we do instead. We do not, in fact, have flops being fed by the lots. For starters, we have transparent latches instead of flops. So with that, and for a second thing, we put them in the interconnect. The interconnect is where all the time is spent in a programmable device. The lots don't matter. And in general, you're clearly going to want to spread your state elements pretty uniformly in Z or in T, because you don't know where the signal is going to be when the subcycle clock hits you. You want to make sure you can grab it with the state element at that time and not waste time. So rather than have to go back to the end of the third lot at the beginning of fold 2, what we can do instead is send the signal all the way to the doorstep of the fourth lot, still in fold 1. We haven't wasted any time at all. And then we can close the latch behind us. So what's happened is we've parallelized the sending of the signal all the way across into the next fold with the closing of the latch behind us. This is essentially like wave pipelining, only it's safe. It has the benefits that wave pipelining would have had, but we're closing the latch behind us to keep it always safe. So in this sense, we're giving up no performance at all, or essentially no performance at all, versus the fastest thing that this physical piece of silicon can do, despite the fact that we have space-time and can take advantage of multiple programs and reconfiguration and the area improvement that it confers. So by dropping this collection of latches throughout the interconnect, now it's possible to run at the full speed of the spatial device and yet still be able to have a reliable, dynamically reconfigurable device. One other detail. So you can see that this fourth of these lots is sort of living on the boundary between fold 1 and fold 2. So how do I make sure that he has the right program when the signal shows up? Well, what I can do is selectively decide to take that one guy and have him have the same program in fold 1 and in fold 2. As a result, whenever that signal from fold 1 shows up, that lot can begin processing. By doing this selective bit of extension is our buzzword for this. By extending objects selectively, I can make sure that each object is ready when data arrives at its front door. What that also means is that the entire chip can always be running at the speed of light of our chip. Speed of light in the sort of the relativity sense of that. Just as you saw these diagonal lines, the lines that go with light cones and relativity and so on, there is a top speed at which signals can be physically transmitted across the physical fabric. We can maintain our computation at that top speed, giving up nothing by having transparent latches that close behind the wave of the signal. And this also means we're giving up almost nothing in the density of the device, being able to pack things into multiple folds. So here I've drawn for illustration a collection of extended things on the critical path. I will mention for those of you who are more EDA expert, since this is based on sequential timing rather than combinational timing, the number of sequentially critical paths is extremely small, so the number of things that have to be extended is extremely small. That's a detail. In any case, looking at fold 0, all of those other blue ellipses can be entirely independent computations of this thing on our critical path. And I can reconfigure all of those things to be green, so they can use the full 12 folds of the device and do whatever they want, independent of this critical path. So I'm giving up nothing in order to get the full 2 gigahertz performance of the fabric. And of course, I can reconfigure the guy on the left to be green as well. So just like with wave piping, we basically have this advancing wave of computation for what's on the critical path, and everything else can be reconfiguring around it. So we're able to get almost full utilization of the 12 subcycles, despite the fact that we're getting the highest performance at the point. So this extension I talked about, in fact, only relatively infrequently happens inside LUTs, since it's in our system's interest to use the muxes, of which there are more rather than the LUTs. We in fact try to arrange things in such a way that the thing that has to have its program be held from one subcycle to the next is typically in the interconnect, which means it costs almost nothing. Which means that you can reuse almost everything, almost always, while still running at the full rate of the underlying circuit. And I ought to have mentioned that our wires are much, much, much shorter than spatial wires, because we are legitimately in 3D. What it means to be in 3D is that the expected length of our wires drops by a factor of the square root of the number of folds, which with 12 folds is about 3.5 or so. So we end up getting 2 gigahertz logic, very short wires, very high density all at the same time. So extension is a big deal. We think it's fundamental to building this kind of dynamically reconfigured device. We use it pervasively. It hides the boundaries of the subcycles and makes our system look like time is continuous, that we can move objects to have any z coordinate we like, and then just extend around it to make sure that this object can sit at whatever z we like. It does mean that you lose the occasional fold for an occasional object, but just occasionally, so it costs essentially nothing in utilization, and it removes that quantization effect and the timing tax of the configuration itself. This allows our designs to run at the highest foldedness we can manage. More folds is always better. I believe this is vital for high-performance configurable computing. I think this is an absolute necessity. Okay, moving on to a couple of other topics that I'll touch on much more briefly. Sorry, I mean, I started a little bit late. Excuse me. We have built our system entirely on sequential rather than combinational timing. And I'm not going to dive deep on that here, but I'll at least touch on it. So here's your basic circuit you might be trying to implement on a programmable device. In time, in this case, going from left to right. What happens in this unfortunate circuit is that because the stages are so imbalanced, your clock is entirely determined by the clock cycle between A, B, and C. And what that means is that the clock cycle that has D in it is just going to waste time, because you're going to have a very slow clock, slower than you'd like, to be able to accommodate A, B, and C, and so you waste a whole bunch of time with D, and E, and F. And unfortunately, just about every CAD system, be it an ASIC CAD system or an FPGA CAD system, looks at things this way. And yes, there's retiming, but people often don't use it because they then lose track of how it is that their test benches look and what the names of signals are and so on. We approach this problem somewhat differently in Spacetime. The fact is that the only delay that actually matters to you, the user, in this picture is from the input to the output. Since the internal things aren't necessarily directly observable to you, the only requirement I have to maintain, and we'll talk about how we get to names and debug and so on in a second, but the only requirement I have to maintain is that in 4 cycles, I can get from the input to the output. Given that, I have total flexibility to move things in time as I see fit, and still be able to try to meet your functionality and timing requirements. So what we're going to do is say, okay, I can go 4 times around the torus, and as long as A is before B, and B is before C, and so on, as long as I maintain the topology, the causality of the circuit, I can put those components wherever the heck I want. I can slide them freely up and down in Z, and we do. And we do that as a way of optimizing area, performance, power, all other sorts of considerations. We have total flexibility about where it is we move stuff. This makes it much, much easier to close timing. Because all of a sudden, instead of being poisoned by completely artificial requirements of trying to keep your flops where you said they were supposed to be, we're instead maintaining only the actual requirement you had in this circuit, which is it took 4 cycles to get from input to output. As long as I maintain that, I met your requirements. Why shouldn't I use the flexibility of moving things around? And I can slide the flops and the components like beads on a string. I don't have to retime. Doing retiming will change the topology of your circuit and make it harder for you to debug. What I can do instead is to slide the flops just as I'm sliding the components up and down through time. This allows us to make it easier to close timing, to tell the user what the real timing problems are. It's completely artificial to say that ABC is a critical path. It isn't. ABC, D, E, F is the only path in the circuit. And if that's not critical, it's a placement not flaw if it can't meet your timing. So this ought to make it much easier for the user to close timing, and that's exactly what we observe. A small digression about state elements. Well, indeed, we have physical state elements, or our physical parts too. We have the latches I talked about, and so on. State elements don't matter. They're simply a notation to be able to name values. You want to be able to say to your language, I don't want the value this time. I want the one from the time before, or the one from 2 times before. The way you do that is by sending it through state elements. But that's the only real intrinsic utility that those state elements have. They're really just a wire in Z in space-time. A state element is just a way of sending a signal up. While we still have to meet the externally visible timing requirements, we have huge flexibility to reschedule operations freely. And we have very fine resolution of time. The fact is we can move things continuously because we can schedule whatever we like. And even looking at the fold boundaries, those are something like 500 picoseconds. Incredibly fine by comparison to the resolution of user cycles. As it turns out, and this is a subtlety, but when it matters, rescheduling in a space-time setting, rescheduling and retiming are equally powerful transformations. But what we're doing is not retiming. Retiming changes the net list, and we're not changing the net list. What we're doing is we're sliding things in time, and that's all. So that means we can preserve your simulation behavior exactly as you specified it. We can preserve your notion of state and names. We can basically move your state element in time and preserve the order, including your state element, by moving things around in space-time. One more aside that's more important, I think. People talk about parallel computing in some of the talks at this conference, talk about parallel computing. My opinion is that parallel computing isn't about parallelism. The whole notion that it is parallel computing is a misnomer. Parallelism doesn't matter. It's about rescheduling computations while maintaining correctness. That is, here I have a pair of computations. Do they have a temporal dependency on each other or not? That is, do I need his answer before I can compute anything or not? If the answer is no, that is, we're independent computations, then I can now do forwards, backwards, or in parallel. Parallelism is just a special case. The fundamental notion here is reschedulable computation. If we start to look at computations in terms of those that have temporal dependencies and don't have temporal dependencies, that are reschedulable and are not reschedulable, that's a perspective, that and a 3D perspective we're offering in space-time, that's a perspective that allows you to transform computations into a framework that allows for automatic parallelism. By rescheduling to be serial or parallel or forwards or backwards, as is most appropriate. So this is a cornerstone of what I think will be the next step in computation. Okay, let's talk about really high performance for just a second. So here are our 12 folds once again. We have our 500 picosecond fold. You want to do something at 500 megahertz, something you basically can't do in an FPGA. So we're going to be 4-folded. That is, you have only time to do 4 folds before you start again. Which means I've wasted 8 of my folds. Well, as long as I've wasted 8 of my folds anyway, can I use them to do something useful? And the answer turns out to be an interesting yes. We have an internal buzzword we call looperness, which is basically what is the size of the tortoise? How many folds is it? So foldedness is how many folds per user cycle. Looperness is how many different programs do you have per gadget. In this case, they're both 4. But what I could do is to unroll 3 copies of your same circuit, so 3 cycles worth of your circuit. And what I'm going to do is to take the output of the first one, the 0th one, and send it to the first one, the output of the first one, and send it to the second, and so on. Now what I have is something that's still 4-folded. It still takes only 4 folds per one of your user cycles, but now I'm using all 12 of the folds. So now I'm 12 looper, and it's periodic only every 12. Why is this a good thing? Because now, instead of having the very tight constraint of whatever loops there were in your 4-folded implementation that might have constrained your 500 megahertz, now I have all of the entropy, all of the flexibility across 3 copies to be able to make that connection easily and to be able to get much higher performance. So it's far easier to close time it on a 500 megahertz circuit by doing this rescaling, as we call it, than it is to have just the one 500 megahertz design. Having circuits that run 500 megahertz isn't enough to be able to get a 500 megahertz design on a programmable device. You have to make the wire short, Spacetime lets you do that, and you have to have the flexibility of rescaling as a way of giving yourself the flexibility for how much you want to route from this state. So this provides easier timing closure and improved routability, and it lets us get back some of the cost of using only 4 folds when you're doing 500 megahertz logic. It also allows a second interesting magic trick. Suppose that you have some 500 megahertz logic and you have some 166 megahertz logic. Well, since in Spacetime, the rescaled 500 megahertz device has a 500 picosecond fold, and the 166 megahertz design also has a 500 picosecond. These are both in the same clock domain from our point of view. They can use that same 2 gigahertz clock, which means I can merge them, which means that place-inbound now has the flexibility to mix and match those guys in 3D freely to get much higher performance, fully scheduled clock crossings, and so on. So we do this pervasively as well, taking different clock domains that might be mergeable and trying to find a way of rescaling them so that we can merge them to get better results. I realize all this is pretty technical. I hope at the very least what you take from this talk is there's a lot more to making this stuff work than just dynamic reconfiguration. There is a lot of machinery necessary to get to this device. But what it gives you is an incredible area benefit, incredible performance benefit, much higher memory throughput, much reduced memory latency. So I'm just giving you through the tip of the iceberg of all the different stuff that's required to make all this go. Let me talk just a tiny bit about the software. We have internally a mantra we call hide the revolution. We want to enable our users to use Spacetime without having to change their design methodology. So we want to be able to take pre-existing RTL and SDC and automatically map the designs to Spacetime as though we were just an ASIC or an FPGA. It should be unsurprising that the trick to this, and this is just a key observation, is view the chip as 3D. Everybody before us who tried to build a dynamically reconfigurable device treated space separate from time and used something like a placer to place things in space and used something like instruction scheduling to set the instructions in time. We most definitely don't take that view, and I think that view is fundamentally limiting. I think that cannot work well. Instead, we treat the whole thing as 3D. We can place all of the objects in 3D. We know what time it takes to get from one point in XYZ to another point in XYZ. To do placement in 3D really isn't that much harder than doing placement in 2D. Even doing placement in a 3D torus isn't that much harder than doing placement in 2D. And so in one fell swoop, by viewing this device as 3D, all of a sudden, we were the first to have an actual solution to the software problem for how it is that you compile a design into a fabric like this one. I will make the observation. This is true for multi-core also. Multi-core devices are also a Spacetime device. It's just nobody's noticed. You have a collection of cores, each of which has a collection of instructions. How do you compile a design into multi-core? Nobody knows. And the reason nobody knows is because they're viewing placement onto the different cores as placement, and they're viewing scheduling of the instructions as compilation of the instruction scheduling. That's broken. What you want to do instead on a multi-core device also is use a 3D placer, and use a 3D placer to place the instructions in 3D. Just what we're doing here. What's funky is that the geometry of this Spacetime isn't Euclidean, and it isn't Manhattan. This comes from special relativity, and it's Minkowski, which means that components' sinks must be in their source's light cone. What does that mean? All right, buckle your seatbelts. So we'll start in 2 dimensions. I have an x coordinate and I have a t coordinate. Suppose I have a component that doesn't move ever. It sits at a location, and it sits there forever. So its world line, its history, looks like a line that goes vertically. It has the same x coordinate at any t you might be asking the question. Now let's imagine a component that's moving at constant velocity. So dx dt is constant, therefore it moves in a line. Or it might be going in the other direction. There's a maximum speed at which any component is allowed to move, the speed of light. And there's a speed of light on the fabric as well, the maximum speed at which a signal can propagate. According to Einstein, the only way you can maintain causality in the universe is make the speed of light a fundamental speed limit. Everybody inside the light cone, as it's called, allows causality to be possible. If I can send you a signal, then I can be a cause for your effect. Otherwise, I can't possibly reach you in time to have any effect on your outcome. Causality is impossible outside that light cone. Moving that up to 3D, now we have X, Y, and T. Again, I have a component, and here is its light cone. So any other object in this universe that I want to have an influence on has to be in my light cone somewhere. It has to be something I can reach with a signal that goes no faster than the speed of light. Okay, now let's bring this back to placement on our chip. Well, I have some second component that I'm supposed to drive with a signal of mine, and it's not meeting timing. And what it means not to meet timing in this world is that it's too far away, its delta xy is too big for its delta t. What should I do? Well, on a 2D chip, when you can't meet timing, the only thing you can do is shorten the wire. Somehow you've got to pull the component in. And of course, that's an option in space-time as well. But that's not the only one. The fact is, any place in this light cone is as good as any other. I can as easily make the connection longer, as long as I give it more time to get its work done. Or I can make the connection shorter. Any place I like in this light cone is as good as any other. And it's pretty easy to capture in an analytical geometry fashion what the requirements are. I have to make sure that every sink of every source lives in the source's light cone. If I satisfy that for all components, I have met timing. I can capture absolutely everything about timing correctness in this formalism. It's simple, and it fits inside a place and route system. And that's in fact just what we're doing. Our place and route system is aware for each component, all of its sinks better be in its light cone, all of its sources better be in its other light cone, and that might lead to a familiar picture. This is why our logo is what it is. These are the light cones upon which our entire system is based. With the catch, of course, that our space-time cones live on a torus. So, since every cycle is going to repeat, what that means is that a component in fold 0 has its cone widen as it goes around the torus, which is a little weird, but still readily capturable with a mathematical formula that can go inside a placer. That's exactly what we've done. Okay, I'm running out of time. I think maybe, well, a little of this next to go through. So, just briefly to touch on a couple of the other myriad issues we had to deal with. Excuse me, we are still dealing with. Clearly, designs with multiple different clock domains are ubiquitous, caused primarily by I/O standards, which have their own individual clocks, but also by IP modules that might require a particular clock and so on. And you need some way of transmitting data between domains. Metastability is, of course, the issue, and it's fundamental and unavoidable. What should you do? And there's pretty much one mitigation strategy, and that's time. You have to wait in order to mitigate metastability. And the longer you wait, the lower the probability of metastability. I'm sure everybody knows that, right? And there are three common ways to do this in non-space-time parts. You either have an asynchronous FIFO to do the crossing, you have some sort of dual clock RAM to do the crossing, or you have some kind of chain of state elements like clocks so that you can have enough data. And we have a version of each of those three things in space-time as well. So we have built asynchronous FIFOs in every single SerDes in every parallel I/O to try to push that annoying asynchrony to the boundary. The reason we want to push it to the boundary is that we can take unfair advantage of having things that are in common clock domains by merging them and allowing place and route to have full 3D flexibility. So it's in our interest to try to push the asynchrony out of the way where we can. We, of course, have dual clock RAMs. Mostly we have single clock RAMs, but we have some dual clock RAMs as well to permit this. And, of course, those dual clock RAMs, when we're not using them for clock crossings, are dual-ported per subcycle, which means they look like 24-ported 2 gigahertz RAMs to do. So pretty high-performance gadgets. Terabytes of throughput per second. And, of course, you can have a chain of state elements. But here we have an advantage over a spatial device, over a classical FPGA. If you need to wait for tau, nanoseconds, in order to reach your level of comfort for metastability, on a spatial part, the only quantum you have for measuring time is your user cycle, which is typically 3.5 to 6 nanoseconds. So if what you needed was to wait for 4.2 nanoseconds to feel comfortable, and your quantum is 6, well, too bad. Well, in our case, we can have a state element at every fold boundary and have a 500 picosecond resolution, which means, in fact, we can wait much less time and you can get lower latency and thus higher performance in these clock crossing devices. So I think I'm going to skip the next bit. Well, I'll do this one as well. Just a second. I will just make the point, without going through all the stuff on the slide here, is that I find it very amusing that people refer to us as having a virtual 3D. I hope this talk is helping you to see why it is that dimension is as real as Einstein's four-dimensional universe, right? so that we're in a real three-dimensional space where a movie takes 3 coordinates to specify everything. Ironically, there is something that's virtual on our part, and it's the clock. When you are running your stuff at 333 megahertz, there actually isn't a 333 megahertz clock on our part like there would be on an FPGA. We have a 2 gigahertz clock, and we're emulating your 333 megahertz clock. What's virtual on our system is the user clock. What's physical is the third dimension. Okay, let me talk a little bit about power. Power is an interesting issue in space-time. There are 4 pieces to it. Static or leakage power, dynamic or user power, as we sometimes call it, I/O power, and then overhead for the reconfiguration itself. Let me talk about these in turn. You know, people often, when they first hear about space-time and see the 2 gigahertz clock, think, oh my God, the power is going to be ridiculous, and that's only exacerbated by the fact that some of the early work by others on dynamic reconfigurable devices, where they pipelined the reconfiguration with the computation, really does burn a tremendous amount of power, and that really isn't a practical solution. We went briefly down that path ourselves and realized it wasn't practical. First of all, we have much lower leakage. Because a space-time device is about 1/3 the die area of an FPGA for a function of a given size, that's our empirical experience. And leakage is becoming dominant in advanced process nodes. Having a chip that's 1/3 smaller is a big deal. And so our leakage is actually not just an advantage, but a potentially significant one. And that's more and more true as Moore's law persists. Now let's look at dynamic power. We think, well, surely the dynamic power is going to be terrible, right? It surprises me that electrical engineers jump to that conclusion, and it turns out it's not true. Here's why. So let's imagine we have a Zytera FPGA, and it has 8 LUTs, and they're all running at 200 megahertz. So they're doing 8 programs worth of computation in 5 nanoseconds of user cycle. In a space-time device, you might instead have 1 physical LUT that's running at 1.6 gigahertz that executes 8 programs. It too is running 8 programs in 5 nanoseconds. That is to say, both of these circuits are doing the same amount of work in the same amount of time. Which would suggest they use the same amount of dynamic power, actually. Except for the fact that our wires are so much shorter. Our wires are 3.5x shorter. So in fact, space-time dynamic power is an advantage, typically, versus that of the FPGA. It's not as big as that of the leakage power, which is a factor of 3 in area. But the fact is, we would have done the same amount of work were the wires to be the same length, but our wires are significantly shorter and we're doing the same amount of work. And therefore, for most situations, the dynamic power for the computation can also be lower with space-time than it is for a spatial device. Surprised, huh? I/O power, well, our I/Os are pretty much like FPGA I/Os. They're industry standards. We have to support them too. No material advantage, disadvantage is about the same. And that brings us to the 4th term, our liability, which is the reconfiguration tax. We have the overhead of the reconfiguration machinery itself, and that is undeniably costly with power. Now, of course, we use that circuit a zillion times, and so we're optimizing it severely, and in fact, with each generation, we're making significant improvements there. That said, it definitely costs us overhead to do the rapid reconfiguration. But what that means in practice is that we have a horse race between a significant advantage in static power and a modest advantage in dynamic power, and a significant disadvantage in the reconfiguration tax, which is 0 for an FPGA and is significant for us. And in fact, at the moment, those are pretty balanced. And longer term, we have very good reason to expect that this ends up being an advantage for space-time. So while our power doesn't have current hope of being an ASIC class, we actually think we will ultimately have somewhat lower power than FPGAs for the same computation because the leakage is rising faster than the cost of the reconfiguration. This is my one sort of marketing slide, but it's also a technical slide, and that is, why bother with all this incredibly complicated machinery? Because the wind in every direction is so large. The fact is, since we're using single-ported RAM cells, we have twice the memory density. We have 2.5 to 3x, the 2.5 is conservative, to 3x logic density versus an FPGA. We have more than 3 times the memory throughput because of the space-time memories you saw before. We have, this is an old slide, almost 4x the DSP performance. Small aside on that, this morning's keynote talked about GPUs versus FPGAs and showed that the FPGA was able to do about 10x the throughput on a FIR filter, getting to something like 1.7, 170 mega samples per second. We have more than an order of magnitude advantage over that. So an FPGA seems to have an order of magnitude advantage over a GPU, which we think is great. We have an order of magnitude, again, advantage over the FPGA with space-time bit space. And finally, the logic performance, since we can really do real stuff at 2 gigahertz and do it all the time, we have a 6x logic performance advantage. So really significant advantages that lead us to call this something other than an FPGA. It's a programmable logic device, undeniably, and we're proud of that, but it's a new kind of programmable logic device, just like FPGAs are different from CPLDs. We see our device is a 3PLD, a three-dimensional programmable logic device that manifests these changes. All right, the big finish. I hope this showed, at least briefly, that Spacetime can significantly improve density and performance and memory and DSP. And it's not intrinsic that it costs extra power either. We map designs into 3D using the math of spatial relativity. Basically, we have a replacing route system use the geometry of a 3D Minkowski spacetime. But given that, it now looks like a fairly traditional placing route system, which is why we're able to take traditional RTL and stuff. This is the big trick. Dynamic reconfiguration is a really good idea. A lot of people have had it, including us. But it's just the first step along an actually quite fascinating path, and we've made significant inventions all along the way. And there's an awful lot of advanced space-time machinery to make this all work. Everything from transparent latches in the interconnect to extension, to rescaling, to rescheduling, using state as just Z wiring, doing our voice out, and 3D Minkowski geometry, and 100 more I could list. This general notion of static scheduling, of recognizing the difference between reschedulable computations and non-reschedulable computations is important. Being able to view computations in this 3D way, where space and time are unified, opens a perspective on computing, on parallel computing, reschedulable computing, that we see as a promising avenue to getting us to that holy grail, getting us collectively that holy grail of taking something that looks software-like and compiling it onto a massively parallel high-performance paradigm. In my opinion, this is a powerful alternative perspective from the more traditional one of parallel computing, as a means of avoiding the massive parallelism we know we can do. Maybe see what's coming. Thanks. Keeping it up until 3 o'clock. Thank you very much. I'll take a couple of questions if there were some.
Yes, are there any questions?
Very fascinating stuff. Something that I don't
Me too.
If you have block balls, and if you run at a block rate, which is typically 6 times faster than a typical FPGA, then your speed of light or the speed at which you are on 72. I can understand why you run faster by forcing the block to be very fast. But I don't see when you say the space, since for every crossing element, for every part of each call, you have to have the context information of what logic it computes as well as where it gets connected, and all of these are literally bits of information. So I can see why you're faster, and of course if 73 is the speed of light, of how much faster you can get, getting these numbers of being 3, 4, 6 times faster, I can see why this is realistic. I don't see why this is smart.
Okay, I don't know if I can capture all that was said, but let me see if I can parrot back some of what you said. You see some of where we're getting our performance, but not where our speed of light improves, and you also make the observation.
I can see where you're getting your performance in terms of speed.
Okay. But the area benefit was the area. Sorry. Okay. Let me explain. So where does the area benefit come from? Two observations need to be made. First, clearly the majority of logic that we're running is running much less than 2 gigahertz, right? So we're assuming that there's logic running at FPGA type speeds of 250 or 300 megahertz or whatever, so we can use multiple folds. For a LUT, just to take the LUT as an example, even though the mouse doesn't have more. On an FPGA, you need a physical implementation of a physical LUT gadget for each of 12 computations, and you need the config bits for each of those 12 LUTs to do 12 computations. In our case, we need only one implementation of the physical LUT, but we do indeed still need the 12 sets of config bits. But the config bits are cheap, because the config bits are cheap for two reasons. One, we're building basically little RAMs that have 12 rows of data. The overhead to add additional rows to that RAM is significantly less than just the rows of bits. The bits themselves, after you have all the decode logic and all the nonsense that goes with the RAMs, the incremental cost of adding additional rows turns out to be actually quite modest. By by way of an empirical number, going from 8 folds to 12 cost us something like a little less than 10%, 9% die size increase. So it's really quite modest. But the second thing is less obvious and just as important. And that is, routing in 3D is so much easier than routing in 2D that we need many fewer config bits to get the same degree of rountability. And in fact, we have approximately 1/5 the number of config bits per LUT that a Cytera part has. And for the same amount of rountability, just because 3D is a nicer place to be.
So I think I understand that the programming model is to not think about it as a 3D, or not to think about the times changes that are happening. But the engineering me wants to know why 12.
The answer is more marketing-based than it is technology-based. Let me describe it. We try to look basically at the spectrum of things people try to do on chips like this, be it ASIC ASSP or FPGA. In fact, we're being used in both FPGA-type apps and also ASIC ASSP type apps because we have performance to make that possible. So we were reluctant to take on making the physical circuits go much faster than 2 gigahertz. We figured, well, Intel can do them at 3 or 3.5 gigahertz. Let's give ourselves 2x margin and not kill ourselves. So 2 gigahertz seemed like the right thing to shoot for. And then the question was, how many folds can we get away with and still be able to use most of the folds most of the time? And that was basically based on marketing input. And it turned out that 8, 10, 12 was about the right neighborhood. Of those, I picked 12 because it's useful that it's divisible by 2 and by 3. And for the rescaling that I showed you before, it ends up being convenient having the additional budget.
How's the place and load time for 3D fabric compared to the FPGA's 2D?
So the question is, what does our place and down times look like compared to those for FPGAs? And at the moment, candidly, lousy. At the moment, our runtimes are slow. But I don't believe this to be intrinsic. There are pieces of the problem that are actually harder in 3D. But there are also pieces of the problem that are actually easier. So I think we're within sight of having that be competitive or better. At the moment, honestly, we're somewhat worse. But not hopelessly so.
In your estimate of dynamic power, you seem to have failed to account for the fact that in a conventional FPGA, you don't change the state on every clock cycle, maybe only 15% of the time. Why not? Right.
So the question was, in my dynamic power calculation, I wasn't accounting for the fact that almost everything on an FPGA is idle, and that very little of the logic is actually doing anything at any given time, which is odd in its own right. And I guess I have 2 comments about that. The first is, if 85% of your chip is idle, you should do better synthesis. What that means is that it was possible to build a version, it was almost truly possible to build a version of that circuit that has much less logic than the one that has 85% of it being idle. But the second thing is, there are more precise answers. There are really 2 cases. The one case is that we treat the logic in 2 different locations, in 2 different folds at the same XY location as uncorrelated. And the other situation is we treat it as correlated. To the extent that you end up treating, and there's no intrinsic reason really that it need be correlated. To the extent that it is uncorrelated, the flickering that we see between adjacent subcycles is analogous to the flickering that you'd end up seeing between looking at the same wire in adjacent cycles. So for logic where we can treat the adjacent subcycles as uncorrelated, in fact we're paying no overhead. The sub-problem, however, you allude to, which is real, is in the situation where it's highly correlated, where you end up having to take the extreme example, you have a block of logic that does nothing for 100 cycles in a row. That costs nothing in power on an FPGA, and that definitely costs power for us. And with that, it was just too much to get into in the talk, but in fact, we have sub-cycle clock gating machine to deal with stuff like that. So what you really want to do in that situation, and we do, is to have the ability to take individual routing elements and be able to say, preserve the value that you had in the previous subcycle and don't listen to your input. And we in fact have the ability in a relatively fine grain to be able to say exactly that, and we do that for that reason. So for the uncorrelated logic, it doesn't matter. For the correlated logic, it does, and that's what we're interested in.
One final question we can allow.
I was wondering, you showed some numbers that were well-rounded. Do you actually have numbers that are like here versus tabula,
came from. So the question was, I showed numbers, do I have actual numbers from benchmark? Where do you think these numbers came from? This is the technical talk. So yes, indeed. These are actually based on customer benchmarks of various sorts. So not surprisingly, being a player, many of the circuits we see when people come and kick the tires are, we implemented this on either Xilinx or Altera. How do you do? And so all of the numbers like that I'm showing in these slides are a function of the average of what we see on real custom results of various sorts.
Hey, we heard a lot of space and time, the speed of light. What I have here is a little bit of the Orion's belt, and this is 42 stars, and how it is actually projected. If you take a camera picture, that's the intensity, and it's basic picture in 3D, and this fits very well to your talk. I want to say thank you, and this is after actually out of all